All right, guys, Mass 6500. There's going to be a lot going on this video. I have no idea how long it's going to take, but I try to, keep the videos between 40 and 50 minutes, and I don't know if I'm going to be able to do that on this one. So a lot going on. So hopefully you're watching this at a video where you have time to spend a little extra time, more than likely. What the focus is today. Oh, I forgot music. Daggone it. Oh well. Sure you guys will survive. What I want to take a look at today is what I call the standardized regression model. And guys, when I talk about standardized, at the end of the day, I want you to think about standardizing something in terms of looking at the z-scores. And guys, just a review, if we have a distribution with a population distribution with mean mu and standard deviation sigma, we can standardize a particular value by taking that, subtracting the mean and dividing by the standard deviation. We're going to do some of that in this video. Now, more importantly, why? And it turns out that a major, at least one of the major goals in to take a look at the standardized regression model. So the major goal is to compare estimated regression coefficients in common units. And guys, you don't have to look far in the education community to think about where this would be probably pretty useful. If we were wanting to predict a student's first-year college GPA from a model, an intercept model, which has B0, and a beta 1, which is the coefficient for ACT, plus beta 2, which is the coefficient for SAT. And think about the way that we interpret the beta 1 and beta 2 in this situation. We would say controlling for the other variables in the model, which in this way would be either ACT or SAT. If we increase ACT by 1 unit, whatever the beta 1 is would be the predicted increase in GPA. If we increase the other way, let's go through, let's say we were just focusing on SAT, we would say the controlling for ACT, as we increase SAT 1 unit, our beta 2 would be the predicted increase or decrease, if it was positive or negative, in GPA. Well, guys, the problem here is what the effect is of a 1 unit increase. I think I mentioned in the last video, an increase of from a 30 to a 31 in ACT is much more significant than an increase of an SAT from, say, 1150 to 1151. Well, because we get things that these coefficients that are in completely different units, it's sometimes beneficial for us to standardize the coefficients. So that's what we're going to take a look at. Now, plus we're going to look at a lot more. I'm going to show you how to do quite a bit in this video that's going to be helpful on your homework assignments. So, let me show you what I did. I've worked, I like R. R's cool, but I've done a lot of work with SAS and SPSS in the past. And something that I really liked about SPSS is the following. So To demonstrate this to you, what I did is I just pulled up Google and did just a very simple search on SPSS regression output. And when I go to the images, the first image that I saw turned out to work really, really well. So I decided to visit the page. And you know the mad love I have for the UCLA folks in the stats department. I think I've mentioned that before. I think they just do super cool stuff out there. When I have questions, that's usually, or looking for cool data sets and so on and so forth. That's where I go. So what they've done here is they've used an SPSS data set. Anytime you see the .sav, that is a data set that's been created in SPSS and saved in SPSS format. And what they've done is they've run some stuff here. And actually, I think he is, I think it's a he. I think I looked at that earlier. Yeah, I know it is. What he's done here is he's just run some regression models on predicting science score from math score, gender, social studies, and reading score. And the thing that I like about SPSS, maybe above R, is the compact presentation of the parameter estimates. So what we have here is we can look at the unstandardized coefficients along with what they call beta, which is convenient familiar notation we've used in matrices, and it provides the standard error. But then also it creates what's called the standardized coefficients, which we call beta. And that's what we're going to learn about in this video. It comes on out in this column under T and gives your test statistic. It calls the p-value sig, and then they've included the 95% confidence interval. So what we can conclude here, let's just concentrate, since we're all math geeks, let's concentrate on the math score. So the beta that we're used to calculating and creating and interpreting would be 0.389. So what we would say here is controlling for gender, social studies score, and reading score, a 1 unit increase in math score will give a predicted 0.389 unit increase in science score. Now, this is fine and dandy if these things are all measured on the same scale. That makes them comparable. But when we're trying to figure out which one of these has the most impact on predicting the dependent variable here, which is science score, it's often advantageous to take the units out and look at the standardized measure. So when I come over here and look at the standardized, the z-score, I see that the highest these are comparable. These may not be comparable because of the the example I provided earlier about SAT and ACT. If they're on drastically different scales, a 1 unit increase means something different. When we standardize the scores, a 1 unit increase means exactly the same thing. So this math score of 0.368 has a lot more impact than the social studies score at 0.054. In fact, almost 7 times as much. The reading score and the math score are kind of equivalent. And of course, the female has a negative, and that's just the way they coded. They coded females as 1 and males as 0. So this would say that females, controlling for everything else, females seem to score lower. Their predicted score on science is going to be about 0.10 lower than for males because of the coding. Now, you could also look at the standardized coefficients and come over and look at the p-values. And it's not always the case, but you can see that as these things lower in magnitude under the standardized coefficients, the p-values get higher. So again, it gives us a way to compare things on a standard unit of measure instead of using the units that the measurement was actually collected on. And it's important sometimes in interpreting things. Now, let's get into a little bit of theory, and then I want to go. I want to come back and I want to show you some things about how we can replicate this in R, and some problems that we run into. So, guys, let me go back to the white. All right. Now, another issue we run into are what we call round off errors, which can be significant. Now, I don't mean statistically significant. I just mean that they can be significant in the context of kind of messing with the final calculations. If you think about the way we make our calculations using matrix notation many moons ago, actually not that many moons ago, you remember that we can find our beta vector by taking the product of these matrices. Well, if we focus in on this part right here, where we take the inverse, when the elements of this product differ substantially in order of magnitude, then we can get a situation where round-off errors become extremely problematic. There's also a situation where when we get variables that are highly correlated, and we get into something called multicollinearity, which is going to be a topic we're going to get into next week, we get in a situation where the calculation, taking the inverse of this, creates round-off errors, and it creates issues with calculations. So, you know, lots of reasons to study these standardized regression models. So again, the two major reasons. It gives us a way to compare estimated regression coefficients in common units when the units drastically differ in magnitude, and it also reduces what we call round-off errors when we take the inverse of the X transpose X matrix. Now, just to give you an example, what if I wanted to predict the weight of a child? And let's say, for example, that we're focusing just on, you know, whatever 10-year-old kids. And I'm just saying 10-year-old because that's how old my kids are. And we have an intercept model. And let's say x1 is the height of the child. And we have a 2 predictor model. And x2 is the year that the measurement was taken. Well, let's say that these are in inches, and the data that we're collecting, let's say, of course, the weight would be in pounds, and let's say the pound is, you know, 100 pounds, and let's say the height is, you know, 49 inches, and the year this was taken was 2012. Well, you can see that these measurements are on drastically different units, and could create problems that I talked about before. Okay? Now, as shown in the SPSS output that I just showed you from the UCLA site, it creates a standardized coefficient, what we call beta. And the way these things are calculated, or the way that the most agreed upon method of calculation is called the correlation transformation. And what the correlation transformation does for us is it makes all entries Well, of the matrix X transpose X, the inverse, assume values from -1 to +1, creating less of these round off errors. So guys, you know, if we have a model, for example, we're going to have a situation where our variables are in drastically different magnitudes, and the measurements for x1 and x2 are drastically different in magnitude, and we're going to create these round-off errors that we talked about before. I was teaching last spring. I taught a 3500 class here on campus for undergraduates, and we ran into this. It was kind of cool because it caught us all off guard. And I wish I could come up with the example, and I'll try my best to illustrate to you how this can actually happen when you get into a drastically different magnitude in the variables. All right, gang, so let's, how do we do this? First of all, let's concentrate on our y's. And to standardize our y's, we would just take each y sub I minus the mean divided by the standard deviation, where, we should know this, but I just don't want to leave any stone unturned. Where the standard deviation of our y's looks like this. For our x's, it's a little more complicated. So for x1, up to xk, so we have k predictors. And let's run this j from 1 all the way up to k. So I'm going to use j as the subscript. Our standardized measure can be taken by taking each x sub I sub j minus the mean for x sub j over the standard deviation for the jth variable, where s sub j is the standard deviation and calculated exactly the way you would think it would be. So we take each entry in the jth variable minus the mean for the jth variable squared divided by n minus 1. Now this brings in what we call our correlation transformation. Guys, I'll tell you, the correlation transformation is not what SPSS uses. The standardized coefficients that they create there is just a straight z-score transformation. The correlation transformation seems to be more theoretically solid, just seems to be the wave of the future, if you will. So what we do here is each y sub I, and we let this new variable, this new standardized variable, be y star. And it just turns out it's just 1 over the square root of n minus 1 times the z-score. Okay? And you thought this stuff was going to be hard. So x star, and this will be for each I sub j, will be 1 over the square root of n minus 1. And we take the z-score for each of these. And I'm going to illustrate this for you. And what we actually end up getting is we get what's called, you know, after creating these, and we create our model, we get what's called a standardized regression model. Our standardized regression model is what I call a non-intercept model. And I'll try to explain that in just a second. But non-intercept just means we don't have an intercept. So our y's down to our kth predictor. Don't forget the star, Douglas. Plus our error. So again, notice that there's a, a non-intercept. And the way I like to think about this is the beta 0 is just essentially the mean of the y's. And then, I mean, that's going to be the prediction when we put all x's equals 0 in our model. Our best prediction of beta 0 is going to be the mean of our y's. If you look up here in our z-score, if we replace y sub I with the mean, we're just going to get 0. Of course, 0 times 1 over n minus 1 is just going to be 0. So at the end of the day, our beta 0 turns out to be 0. So there's no need including it in the model because it has no effect. So guys, we call the standardized regression model the non-intercept method. Okay? Now, the rest of the video is going to be on using R, and I'm going to show you some new stuff. So I'm going to minimize this because I don't need it. And what I want to do is I want to go back, and notice I've got R up, so go ahead and make that happen. And I want to replicate this. Now, something I don't think I've shown you before. When I look at this, I see that the data set that they've used is this HSB2. And if I click that, what's going to happen is it's going to save it as HSB2, okay? Now, if on the Mac, I can go over here to my download, and there's HSB2, which I can bring to my desktop. The reason I want to bring it to my desktop is that's where I'm going to set my working directory when I get into R. Now, guys, kick your shoes off, prop up your feet. We're going to be here a while, as Uncle Jed would say in Beverly Hillbillies. I don't know. Did he ever say that, really? Who knows? So what I want to do now is I want to open up this SPSS file in R. Well, that's kind of like putting a key from a Chevrolet into a Ford. You know, there's incompatibility issues there, but it turns out there's things that we can do. Now, it turns out there's a lot we need to do. Well, guys, first of all, we know that we've got to set our working directory. And we've got to go get our data. Now, problem is, we're used to using read.csv, and now we've got a .sav file because it's an SPSS format. So what we have to do is we have to install library, tough for a Kentuckian to say, called foreign. Foreign is going to allow us to use something called read.spss. So guys, I'm going to get data, and I'm going to go read.spss. So hsb2.sav, and it's going to read it. No commands, no errors, which that's good. We're going to attach our data, and we're sitting there thinking, oh wow, this is really cool, this is easy. And we hit data, and we see that we get a bunch of garbage. Now, this is kind of a cool data set, in my opinion, because it has student IDs, that's kind of generic. It has gender, it has race, it has socioeconomic status, it has school type, it has some sort of academic program, whether vocational, general, so on and so forth. It has some reading, writing, math, and science scores. And I'd like to be able to perform some analysis on this, but right now it's just mumble jumble. Well, what I can do now is I can create what's called a data frame. So I'm going to create I'm going to call it new data. And I can create a data frame to organize the data that I have now. I think I call that data, that's what I usually do. Yeah, to better organize the data. All right? So now when I type new data, I can see that I have my data set in more of what we see in Excel, what we're used to seeing. Okay? Now we're going to go attach new data. And I'm like, at this point, I'm like, you know what, it'd be kind of cool to find the mean of math. And I find that. Okay? It'd be kind of neat to find the mean of science. And I'm able to find that. Okay? Now, guys, sometimes you get data sets that are so cluttered, even though we've got this now in data frame, we could potentially get what's called a masking issue. Now, the following objects have been masked from the data that I created previously, but now I'm dealing with what's called data frame. What I have found, and it takes a little longer, it takes about 5 to 10 minutes longer, but it just seems to create more stable measures. All right? Now, what I like to do here is I like to take this data set, write it to my desktop, resave it as a .csv file, and then bring it back in so I've got everything in familiar notation. Now, you might say, well, why are we doing all that? Trust me, guys, there's a reason. Some of the calculations won't be stable if we keep this in the data frame as we've presented right here. So what I like to do, there's something called write table command, and what that's going to do, it will take a data set that you have open in R, and it will write it to your working directory, which is our desktop. So I want to take this new data that I've created, and I want to save it to my desktop as, let's just call it math.csv. Now, when I go to my desktop, you're going to see that I have a data set somewhere. Yeah, called math.csv. I don't know why that happened. So I can open this up in CSV format. And I'm thinking, oh, it's going to be cool. Everything's going to work just fine, and it's going to be, the computer's having a slow time getting things done. And I get in this, and I'm like, holy crap, that's not cool. I can't do any analysis on that. I would have been better off keeping the data frame. Well, it turns out it's not a big deal on how to transfer all this text. into data that you can use and actually get back into R. Okay? So what we need to do is we need to come up here to data, and there's something called text to columns. So the first thing I've got to do is I've got to select the first column, go text to columns, and follow the prompts on the screen. So what I'm going to use here is called delimited. And I'm going to go next. And guys, these things are separated by space. And notice when I hit space, it automatically kind of reads my mind in that it wants to separate the entries by space by putting them in separate columns. Now I can go ahead and hit next, hit finish, and you'll see when I'm finished here, I have things in familiar format in .csv file. Now I'm off a little bit. Notice that the heading here is off a little bit, but that's easily, you know, I can just go in and copy that, and I can start right there and paste over, and I can get rid of this column. Now, if I need to. Now let's, you know, there's some cool stuff here, but I really don't need all of it for what I want to do. If I go back and look at what I'm trying to replicate here, you'll see that they're predicting the science score from the math, social studies, reading, and gender. So I'm going to get rid of the things that I don't need. I'll tell you what, let me make that a little bit bigger. Wow, that's huge. All right, so I don't need that, so I'm going to get rid of those. And remember, on ID is not important in the CSV format because it's going to create IDs when we get. Well, you know, as I say that, I guess there are situations where it would be important if we need it. Say we have a extreme outlier and we want to identify the student by ID. So there may be a situation where we need to keep ID, but this is not it. So race, SES, school type, program, we're not using that information. And I don't think we're using the right score, right? Yeah. So yeah, I don't need it. It's just going to clutter stuff up, and so I don't need that. Okay. And centered up. All right, got a cool data set that we can use for our analysis. So I'm going to do a save as, and I'm going to call this math, and save it to my desktop at .csv. So I want to replace what I had before, or if you don't, let's say you want to keep that for some reason. I don't think there's anything wrong with that. Let's just call it a different name, math2. So save it, continue. And now we've got our data set that we're going to replicate, sorta. All right. It's not going to work, and I'll explain why not. So let's quit R. You know, we got way too much clutter going on there. When I'm doing things that are really important, I don't want clutter. I want things very simple. I don't want multiple data sets open in R. I want to keep it simple because the stakes are high and I don't want to take any chance of something happening in R and giving me a wrong calculation. All right, so guys, we go into R and you know, we get to start repeating a process that we've done many times. Data, so read.csv. And we call it math2.csv. We attach our data, and I like to look at the names of the data. So the variables are all capitalized, so I have to keep that in mind. So let's get busy. Let's create our first model, and so I want to do a linear model, and they predicted science. Let's click in. As a function of, I think they put in math first. Then they put in gender, which is called female. And I think they put in next, let's go over here and just double check. That really doesn't matter, but I want to be consistent. So social studies and then reading. Yeah, look at a summary. Let's click that off. Summary of my Model 1. And I'm like, well, you know what? They used SPSS. I'm using R. Both are widely acceptable in performing, finding the coefficients of models. And they both should be consistent, and they both should be the same outputs. And we bring those things side by side. And we're like, oh, crap. What's going on here? SPSS, I would be afraid to estimate how many hundreds of times per day that important information is shared using SPSS calculations. You'd be surprised how many times R is used to make important calculations. Think about the medical field and the calculations are made. And we have the same data set, but yet we have different coefficients. Their intercept is 12.325. Our intercept is 10.32. Now, which one's wrong? Which one's right? Well, they're both right. They're both, neither one's wrong. They're both right. What SPSS does is it does a calculation using what we call the contrast model. And it will set the gender as -1s and +1s, because in contrast, and that's something that we haven't talked about a lot yet, but we will. In contrast, our contrasts have to add up to 0. So they set 1 at -1 and +1 when they make the calculations. Now, so what should we do? I mean, if at the end of the day, well, first of all, when you're conducting your analysis and when you write it up in Chapter 3, when you write up your statistical results, first thing you're going to tell the reader is I used R or I used SPSS to make the calculations. You're going to tell how you calculated and entered your variables into the statistical software package. The reason is because what I'm getting ready to illustrate to you. Now, let's keep that in mind, okay? The intercept is 10.31, which doesn't match up with the intercept of the model that's created over here. So, gang, I'm going to get rid of this. And I'm going to go back into my data set called Math 2. And I don't think I did. Oh, okay, there we go. Let's do 150, okay? And what I want to do here is I want to go up to data and I want to sort this. And I want to do the whole shebang. And I want to recode as the guy from UCLA did. He recoded female is 1. So I'm going to fill down. And every place I see female, I'm going to insert a 1. All right? And now I'm going to code male is 0. Excuse me. And I'm going to save the file. And I'm going to continue. And now I have gender code as 0s and 1s as they did. So I don't need to save because it's already saved. Let's bring up R. Let's grab our data. Attach our data. Excuse me. And let's run our model. So our model, I never can remember. All right, so our model is going to be, let's see, we're doing science as a function of math plus female plus social studies plus read. Now, gang, when I do summary of my model now, lo and behold, we get the same thing. Now, the reason I'm showing you this is because it's it's actually, the reason I'm showing you this is twofold. First of all, it's a nice lead-in to what we want to do with these standardized regression model coefficients. And secondly, I want to show you that explaining to the reader the way that you have coded your data, the way you've entered it into R or SAS or SPSS is so important because of the reasons that just happened. We got completely different outputs based on the way that we entered our data. So now let's talk about how we would make this correlation transformation. Now, again, there's going to be two things going on. First of all, how does R create this 0.3? I'm sorry. How does SPSS create this 0.368, negative 1.01, 0.054, and so on and so forth? Well, what they do is they just use a standardized measure. So what I could do here is I could create a model 2. And let me back up a little bit. If I wanted to create the z-scores for math, what I need to do is just do scale math. And what it's going to do is it's going to create the z-scores for all of the entries in math. So if I do z math, it's going to have 20 entries. And it will, actually, that's actually kind of cool. It actually gives us our mean and our standard deviation. So it's created the z-scores for each of these. So to replicate what happened in SPSS, I could create a model 2. So I could go scale of my y, which is, I forget, is read, right? Let's tell you what, let's do. Let's just copy. All right, so I need the scale of science as a function of scale of math plus scale of female plus scale of social studies plus scale of read. Guys, I can get rid of all this stuff. And hit enter, do summary of my model, and I get the standardized coefficients. Now, just to show you that those are the same, you can see that we have 3.68 times 10 to the negative 1 power, which is the same thing as 0.368, and so on and so forth. So we get the same values. But guys, the technique that I'm showing you is not the technique that SPSS creates. The technique that I'm trying to teach you here, and the one that I want you to use, is called the correlation transformation. So what we're going to have to do to make that happen is we got to do a little bit more work. So guys, what I want you to do now is let's close down R again. We're going to wear R out, aren't we? And go back into Math 2. I'm going to maximize this and make it larger so we can see it, or at least so I can see it. Okay? Now, what I'd like to do now is I'd like to make this, this transformation from zread using, okay, so I'm going to create this new variable called zread, which is the correlation transformation. Now, what I need for each of these is I need the mean and the standard deviation. So I'm going to go over here and create that. So I'm going to go equal, guys, and Excel. We don't use mean, we use average. I'm going to create this for all. And then I want to do the standard deviation. All right, once I get this, I can do a drag over and create the mean and standard deviation for all the variables. Now, to make the Z transformation, I'm sorry, the correlation transformation, remember what I have to do is I have to take 1 divided by the square root of n minus 1. So I'm going to have to go equal square root of, let's see, our sample size here is 100, I'm pretty sure. Well, good thing I checked because it's not, it's 200. So I need to take the square root of 199. No, I don't. I need to take the quantity of 1 divided by the square root of 199 times my entry of 68. Well, let's just do read 68. Really, I'm going to need another parentheses in there. Minus the mean. Which is 52.23. Divided by the standard deviation, which is 10.253. Guys, I can use my fill down. And go from there. Now, would there have been an easier way to do this? Probably so. We could have easily done this in R. We could have created new variables and created a new data frame. And in fact, I think it's probably going to be worthwhile to demonstrate that to you. So guys, anyway, we could go ahead and do this for ZMath and so on and so forth, okay? So if we prefer this way in Excel, and some people do, the reason is data sets I found to be a little harder to save, more cumbersome in R. Data sets are easy to save in Excel. So if you're going to be working on something, you know, day after day after day, I found it to be much easier to save your data sets in Excel, .csv, bring them into R when you need them, and so on and so forth. So that's the reason I'm demonstrating this to you. It's very, very unlikely that you're going to collect your data set Uh, jump into R, perform your analysis, write everything up in one day, and be done. You're probably going to have multiple times that you're going to visit R to perform calculations. So saving things in .csv format in Excel have certain advantages. But let's say that you're one of the lucky ones and you have a situation where you can just make your calculations in R. So what we could do, let's take a look at this, okay? And all we'd have to do is just create some new variables. So I could create zread. By doing what? Well, I would take 1 divided by the square root of 199. Times read. Well, really all I'd have to do is just go times scale of read. So zread should look kind of familiar. That's off a little bit. Now this right here is gonna got me confused. That's kind of why I'm stumbling around. Please use magnification. Okay, that's funny. All right, so gang, I could next. Let's just go Z math. Let's go zread. Yeah, I'm sure you see where I'm headed with this. What else do we have going on here? Science and gender. All right, so we've done the correlation transformation for each of the variables, and the formulas are with the stars and the subscripts. That always gets a little weird, but you can see that we've already done zread, didn't we? Okay. Anyway, we have this. Now, if we want to organize our work, we could create a new data set and use a data frame. And we could have math, read, social studies, science, gender, and then we could include ZMath, ZRead, Z social studies, Z, was it gender that came? No, Z science. Z female. And we could do Z, that's it. So guys, do new data and we can examine our data if we need to. Now, in terms of creating the standardized coefficients using the correlation transformation, we can create model 99, if you will. So we are in the business here of predicting what? Z read as a function of Z math plus Z gender. I don't know why they call that female, not just gender. Z social studies plus Z read. All right, what's going on? All right, we want Z read as a function of math. I don't think it's like in the, well, let's see what happens here. Well, you can see we get essentially a no-intercept model. Not really sure what's going on here. It's talking about the contrast. The response appeared on the right side and was dropped. Okay, that's cool. In model matrix default, MT, MF contrast. Getting into that contrast. Model matrix, no columns are assigned. Okay, all right, so we're good. So when we so for some reason, what did it do here? It dropped read. Now that is extremely confusing. I wonder if it's... Oh gosh, you guys are probably sitting there screaming at me. Oh goodness gracious. Oh yeah, I hear you screaming. We are predicting science. Oh gosh, this is embarrassing. We are predicting science score. All right, so let's. So you don't think it's a good idea to predict read from read? No wonder it says you're an idiot. So let's do this right. Wow, sorry. See, that's where in a classroom people would catch that. So let's call this model 9999. And instead of Z read, we want Z science. And much better. All right, gang. Sorry. First mistake ever. And here we get our estimates. Now, again, this is essentially an intercept-free model because to negative 17 should be clear. And let's compare to what SPSS calculated. Well, guys, you'll see it's the same thing, right? So I'm a little surprised by that. I thought they used just a straightforward. So anyway, of course, as the data set gets larger, you got to think about the difference between just taking the scale and taking the scale times 1 divided by the square root of 199. 1 divided by the square root of 199 is an extremely small number. So multiplying a number by 0.071 is not going to have much effect on it. So I guess that would the difference between the correlation transformation and a standard what I would call a z-score transformation is not going to be as significant when we have larger data sets. Now, if we only have maybe a data set with 5 measurements on each variable, then you could see where there would be a difference. So, well, gang, that's all I got. Sorry for the confusion there. I just dropped the ball on what I was trying to predict, but it's a good thing I found it and didn't have to scrap the video. So, guys, your assignment is going to be up pretty soon, and you're just so you can run through this. I'm going to have you access a data set that's in SPSS format and replicate what we did in this video. So, guys, that's all I got. Take care.